Today, our speaker today is Balazs Barany from Budapest. Are you in Budapest or in Finland?
In Budapest now.
In Budapest. So from Budapest and in Budapest now.
Somewhere in Hungary. That's the.
And the title is typical absolute continuity for all parameter families of dynamically defined measures.
Thank you very much, and thank you for the invitation and the opportunity. I'm pretty sure it would have been much nicer to be in person in Warsaw again, and after the seminar spend some time in Śpiewak. However, I hope that it will happen quite soon. And I need to also begin my whole talk with an apology. Because when ages ago, I spent my first postdoc year in Warsaw between 2012 and 13, I wrote a paper at that time on manuscript on iterated function system with phase-dependent probabilities. However, this paper turned out to be wrong, and I gave a talk about there as well. I can even spot you the exact moment when the proof breaks down, and this error was not really healable in an easy way. So basically, after the publication, after 1-2 years after the publication, I realized this mistake, and already with Michal we begin to correct the proof here, but it was corrected just very recently together with Károly Simon, Boris, Solomyak, and Śpiewak. And also the statement which was valid here needed some modifications on the assumptions on some other cases, but for several cases still remained valid. So what are these things about? So let us take an iterated function system, and from now on our word will be conformal. So we will always assume that our iterated function system contains of conformal maps. For the easiest, we assume that our IFS is on the real line, and our results will be also on the real line. Let's assume now these are C1 plus alpha maps, and we assume that these guys are all of them are contractions. So then there exists a unique and non-empty compact set, which is invariant with respect to these functions. There's a nice dynamics associated and basically Boris living on omega, namely in each of the points in lambda can be associated with an infinite sequence of symbols. So here I have m functions, then I take the symbolic space, which will be the one-sided infinite sequences of corresponding to the symbols 1 to m. And from this symbolic space to the attractor, we can define a so-called natural projection, which is just, let's compose the functions in the order how it's in this infinite word omega and take the limit. So I could have written here whatever I wanted. Of course, since this contractions, this function is well defined. And let me denote the left shift operator by sigma here. And the main question is, what we are interested in is that if you have a left shift invariant ergodic probability measure on your symbolic space, omega, and you push it forward by using this natural projection, so you make it a measure on your self-conformal set. Then the two main questions which we would like to discuss now, that what's the dimension? How can we calculate, when can we calculate the dimension of such kind of push-forward measure? Or when can we say that this push-forward measure is absolutely continuous with respect to the Lebesgue measure? So we are on the real line for Okay, but and for a little bit short, to shorten the notations, whenever I write omega, this can mean two things. Omega can mean, depending on the context, as infinite or a finite word. And if it means a finite word, then this f of omega means the corresponding finite composition of the functions. Okay, so these are our main questions. And when can we say something about these questions? So, for example, from Ruel, it's possible to, Ruel showed, he was looking for dynamical systems, not really IFSs, but basically this is what he proved, that if we have a separation, namely, if you take the images of your self-conformal set with respect to two different maps, then this is an empty set. Then you can calculate the Hausdorff and box counting dimension of this set lambda, which will be the unique root of the pressure function. What's the pressure function? You can see here the pressure. Here you take all the sum over all possible n's composition of the functions, and you take the sup of the derivative. So this basically means here, what is this sum? Basically, by the bounded distortion, this norm here, this is the sup norm, is uniformly comparable with the size of the cylinder. So with the size of the set, which is the image by f omega of my original self-conformal set. So basically, this is a generalization of the well-known self-similarity dimension. So limit exists, lots of nice things, and this is the unique root. Moreover, if we have a shift invariant probability measure, which is ergodic mu, and we push it forward with the natural projection, then it's Hausdorff and Packing dimension, since these measures will be exact dimensional, which means that the limit of the local dimension exists at almost every point and has constant value, which will be the entropy over Lyapunov exponent ratio. This HME is the entropy, and the Lyapunov exponent is, so what it means that the average contracting ratio of the system. But if you don't have separation, then the thing what you can say is that these values, I mean this root of the pressure S and the entropy over Lyapunov exponent ratio is an upper bound for the box counting and upper Packing dimension of your measure. Oh, this is supposed to be mu, sorry. This nu is a mu. So then you have upper bounds. So the question is that under what conditions can we say that this equality is preserved, namely there is no dimension drop with respect to the symbolic space. And there are several cases. The simplest case is the self-similar case. For what there is this nice classic result of Mark Polikot and Károly Simon, in which the transversality method was introduced. I will talk about the transversality method later. So basically, this is the 0-1-3 problem. They showed that for almost every translation parameter, they calculated what the dimension of the attractor shall be. This is log 3 over minus log lambda. And then is the natural measure, the 1/3, 1/3, 1/3, when you gave the uniform measure. You are looking at the uniform measure on the symbolic space and push it forward. When is it absolutely continuous? For Lebesgue, almost every lambda between 1/3 and 2/5. But thanks due to in the self-similar case, the additive structure of the set, then the most recent technique is not relying on transversality, but relying on additive combinatorics. So for example, Hochmann's celebrated result that if between the cylinder sets and between the nth iterate of the functions, there is some kind of exponential, no, sorry, this is not super exponential separation, this is just an exponential separation. So this super is not there. So if there is an exponential separation and your measure is Bernoulli, then you can calculate the dimension, which is still the entropy over Lyapunov exponent. Or this was generalized by Jordan and Rappaport, relying heavily on the results of Shmerkin for general ergodic measures. But these results are basically saying that if you have a one parameter family, then, and this parameterization is regular, namely there are no infinite sequences who are, let's say, begin with the different symbols, but having the same value for every possible value of lambda parameter. So there's no such kind of degeneracies. Then basically these exponential separation means not Lebesgue typicality a little bit more, it means except the zero dimension of set. But value for the Bernoulli convolution basically determined explicitly that the dimension can drop with respect to the entropy over Lyapunov exponent only in the case when lambda is algebraic. So whenever lambda is transcendental, it's strictly larger than 1/2, then the dimension of the self-similar measure with uniform weights, 1/2, 1/2 is 1. Also, there are results for the absolute continuity, like Shmerkin proved still in the regime of Bernoulli convolutions that outside of the zero Hausdorff dimensional set, this will be absolute. I mean, still, I'm talking about the uniform weights case in this regime, except the zero dimensional parameters, it will be absolute continuous. And where you also showed some algebraic parameters where you see absolute continuity. I mean, this is not really some algebraic lambda, but some algebraic conditions on lambda, which with which you can check whether it's absolutely continuous or not. And also Shmerkin and Solomyak proved LQ densities for uniform contracting ratios, and Saglietti, Shmerkin, and Solomyak extended for general. And these results and very strong results on the exceptional sets are really thanks due to the additive structure of the self-similar systems. What about in the more general self-conformal case, when we assume that at least one of our map is not linear anymore? So there's this result of Simon, Solomyak, and Urbansky, who showed that under the transversality condition, if you assume that, then again, for almost every parameters, you can calculate the dimension of the push-forward measures and the dimension of the attractor. Balazs and Schlag gave estimates on the dimension of the exceptional parameters. And the result of Horman and Solomyak, which was about the Furstenberg measure, but basically it's about iterated function systems having rational maps, is stronger in the sense that they need only not transversality, but a weaker condition, still the exponential separation. It's because these rational maps keeps these kind of, not strictly speaking additive, but a groups-like structure, which is very, very useful in order to show such kind of things. But what is the common? Because now from the rest of the talk, I would like to focus on this transversality condition and what was known with the transversality condition. So you let me state the theorem of Simon, Solomyak, and Bansky. So let U be a bounded open domain. This will be the domain of my parameter family, my parameterization. And let us have a parameterized family of conformal iterated function systems in such a way that, okay, now for the simplicity, they also use parametric cases, prove things for parametric cases, but now we assume that it's a hyperbolic system, namely the derivatives of the maps for every lambda and for every x is bounded away uniformly from 0 and 1 for every lambda and every x, and the maps which maps lambda to C1 plus alpha is a continuous. So all the maps here are C1 plus alpha maps, and it depends continuously on the parameters. And if the assumption is, the transversality assumption says that you can find a uniform constant independent of everything, such that if you take two infinite sequences whose first symbol are different, so usually, naively, the images, by the natural projection of these infinite sequences shall be far away, but sometimes they will be very close because of the overlaps between the cylinders. But you assume that the set of parameters for which they are close to each other with the distance r, then the measure of these parameters can be at most constant times r. Okay, this is your transversality assumption, and if you know that, then for every fixed measure, you pick your favorite measure from the symbolic space, shift invariant ergodic. If you push it forward, then it will be exact dimensional with dimension equals to the minimum of 1 and entropy over Lyapunov exponent. Moreover, for those parameter values on the domain of those parameter values where this entropy over Lyapunov exponent ratio is strictly larger than 1, it will be also absolutely continuous. And these are for Lebesgue almost every parameter. So for example, not a naive but natural parameterization of such kind of iterated function system is the parameterization by translations. So you say that by parameterization is that I add to each function some lambda 1, lambda m value. And if you assume that the derivative of all of these functions is at most 1/2, I mean the sup of the derivative is at most 1/2, then you are in business, then it will be a transversal family. Well, basically, instead of this, you can say something weaker. You can assume that if you take the derivative of the two largest functions, so you take the derivative of two largest, where the supranorm is the largest, the two largest functions, and their sum together must be strictly smaller than 1. So some of the functions can have larger derivative than 1/2, but at most 1, and it's very dominates the other functions now. So the sum of the two largest derivatives must be at most. Okay, but the main part here is that we are talking about fixed ergodic measure. So this ergodic measure here is not depending on any parameters, not at all. That's forbidden in this technique. But there are quite natural cases when it occurs that it would be very good to project such kind of measure which depends on a parameter, because this dependence occurs very natural. For example, if you are thinking about dimension maximizing measures or the equilibrium measures. So let's recall what we see in Rouel's result. What was it? That if there is separation between the cylinders, then the dimension of mu equals to S lambda, where this S lambda is the unique root of the pressure function. But what does Simon, Solomyak, and Urbanski's result allows overlaps? And under the transversality condition, of course, this S lambda, since the derivatives here are depend on the value of S lambda is also will depend on the parameter, right? Where the root is taken. By the way, sorry, here should be minimum of 1 and S lambda, not just S lambda. Okay, sorry, second typo. Here it should be minimum of 1 and S lambda, because S lambda, of course, can be larger than 1, and we cannot exclude this. So, but in such a case, when you have in your IFS C1 plus alpha max, then basically there is a unique Gibbs measure whose equilibrium, unique Gibbs measure, who is an equilibrium for this pressure. Namely, if you take the potential function built up by the derivatives of my maps and S lambda. This is the most natural way how you do it. Then there is a unique ergodic shifted variant measure, which now, since the derivatives are depending lambda, it also depends on lambda, such that the cylinders, look at here, the weight of the cylinders are uniformly comparable with the diameter of the cylinders in R, which is uniformly comparable with the derivatives of f lambda, of the function composition f. Okay, these constants here can be made and can be assumed that they are independent of lambda. Okay, by restricting yourself in U on some compact set, so you assume that U is bounded and contained in a compact regime whatsoever. Okay, but we can assume. But here you see that this guy here, this measure now depends on the parameter. And for this measure, this is why it's an equilibrium, because the entropy over Lyapunov exponent ratio for that guy is exactly equals to the S lambda, the conformality dimension, which is the supposed to be value of the dimension of the set. So this is one case where such kind of dependence of the measure occurs. But there is another case, which is the so-called place-dependent measures, which are, well, in my understanding, originated somehow from the chaos game. So, but what's the standard chaos game? So you have an iterated function system, and you have a probability vectors. Okay, assume that all the probability weights here are strictly positive. And what do you do? If you are on your attractor at some point x naught, you toss a coin which with probability pi chooses the function of fi, and then from x naught you step to the position fi of x naught. Okay, so in this way you can easily define a Markov process on your self-conformal set. And this Markov process has a nice unique stationary measure, which is the usual self-conformal measure. Right? This is by definition this is the definition of self-conformal measure. But you can change this definition just a little bit. So instead of saying that pi is a constant value and independent where I'm standing, it's a natural generalization to say, to define the Markov process in such a way that actually depends on my position. So you define pi Hölder continuous maps, which are maps from the attractor to the 0, 1, such a way that the sum of these maps is uniformly 1. And you extend the previous chaos game in such a way that you are in the position x naught. Then you choose the function fi with the probability pi of x naught. Okay, and then you step to fi of x naught. This is your Markov process. And okay, in much weaker, under much weaker assumptions, but essentially Fun and Lau showed that in this case, for this Markov process, also there's a unique stationary measure, shift invariant, ergodic, whatsoever, and this having nice decay of correlation properties, of course. So, which is stationary in the sense that the expected value of G will be unchanged after one step. Okay, so again, if there won't be any overlap between the cylinders, between the F1 of lambda, F2 of lambda, and so on images, then the life will be much easier. But of course, if there are overlaps, still this chaos game makes sense. But the measure, this new measure, is also will be what? This will be on the symbolic space. It will be actually a Gibbs measure, where this Gibbs measure will be associated with the potential phi, which is just the log of the probability corresponding to omega 1 at the position corresponding to sigma of omega. So since the natural projection, of course, depends on the parameter lambda, if we have a parameterized system, then this potential again will depend on so this depend on, and there will be such kind of again a Gibbs measure where the measure of the cylinder will be uniformly comparable with this product of probabilities. And here again, it will depend on the parameter. So there are several cases where it indeed depends on the parameter. Yeah, Miha's comment that it was maybe long before than Fun and Lau. That's I think so. So, however, I'm not sure because Fun and Lau basically studied the exponential decay of correlation. So I'm not sure that under what conditions is the first, but definitely you are right. Barnsley, Demko, Elton also worried with chaos game, but some of the results was just for fixed probabilities. Some of them are with changing probabilities. I mean, place dependent. So it's not really well, clear for me who was really the first figuring out this stationary measure. Yeah. Sorry. Let's now then, so since there are nice and natural examples, let's see now what are our results with Károly, Boris, and Adam. There are technical restrictions which are necessary for us. For example, one technical restriction is that instead of higher dimensional parameter families, like we have seen before, this parameterization by translation, it's Rm, where m is the number of your functions. Here we need to restrict ourselves for one-dimensional parameterizations. That's basically seemingly purely technical. It seems less technical and seems quite important and useful that usually the smoothnesses of the iterated function system are assumed to be C1 plus of. Now we need to assume that in X variable, which is the function variable, not the parameter variable, we have C2 plus delta maps. Moreover, every time when we talk about this map, here is C2 plus delta, we mean that it's uniformly in the parameter, namely all the constant and all the exponents or whatsoever will be independent of the parameter. Also, if you are looking at this guy as a function of parameters, previously it was just assumed that to be continuous. Practically, to check the transversality condition, you needed that it's continuously differentiable. But now, again, to show what we want to show, we need a more regular smoothness. Namely, we also assume that on the parameters, these functions are depending on C1 plus delta A. And also, if you are looking at the mixed derivatives, it's also uniformly Hölder with respect to both the parameters and both the variable X. Okay, so these are kind of increased smoothness properties than the usual setup. But we also assume that our IFS is uniformly hyperbolic, namely its derivatives are uniformly bounded away from 0 and 1. And we assume the transversality, which let me formalize in this way, since we already have a differentiable or even further C1 plus alpha dependence on the parameters. So namely, if you have two infinite sequences, which first symbols differ, and they are close to each other, so they are in the delta distance to each other for some particular value of lambda, then the derivative of the natural projections at this lambda parameter value should be greater than that. So this means that the function graphs of these two natural projections must meet strictly transversally. So by the way, we also showed that under these smoothness conditions, basically this transversality assumption with the derivatives is the same transversality assumption what I told you already with the measures. So there's no big difference. There's no difference between them. Okay, so this is the assumptions on the iterated function system. What is the assumption what we require from this parameterized family of measures? We require that this parameterized family of ergodic measures shall be also somehow uniformly continuous on the parameters. And what we mean by that? So first, the basic continuity says that for every epsilon, you can find the delta such that if lambda and delta are lambda and tau are parameters for delta close to each other, then basically the ratio of the cylinders corresponding to the finite set lambda, then the mu tau and the mu lambda measures of the same cylinder set just differs by e to the power epsilon times length omega. Right? So this epsilon here can be, so this means basically by this inequality that if with respect to lambda, a cylinder has positive measure, then with respect to all the parameters, it must have positive measure. If with respect to a parameter, a cylinder set has zero measure, then it must have for every parameter value a zero measure. Okay, and also these guys are uniform in this sense. The continuity is uniform in this sense. Moreover, we assume that the entropy and the Lyapunov exponent depends continuously on lambda. Of course, in this case, these things are not for free. Of course, okay, the dependence on the Lyapunov exponent. So the still we need to assume, even though we assumed here some kind of uniform continuity for the measure, for this Gibbs family of Gibbs measures, we still need to assume continuity for the entropy. All right, otherwise we cannot have. But if you have this, then, and you have all the previous smoothness properties for the IFS, it can be even less. So this part can be weakened significantly. Then the push forward measure of this parameterized family of mu is the minimum of 1 and the entropy over Lyapunov exponents. Okay. So this theorem was essentially proved by myself and Michal Rams when we were hunting for dimension maximizing measures for self-affine systems, and we needed it. And this is what how we could here disprove what I told you that's wrong. But the absolute continuity was very much missing, and actually it was missing because for the absolute continuity, we need an even stronger continuity assumption than here. Namely, we need to assume that this family of this parameterized family of Gibbs measures is not just uniformly continuous, but uniformly Hölder continuous in some sense. Namely, you can find uniform values, constant and theta, for which the mu lambda measure and the mu theta measure of the same cylinder set is uniformly comparable with e to the power plus minus the distance of lambda and tau parameters to the theta. So this means that this measure is somewhat uniformly Hölder on the parameters. And also, if we assume here that the entropy and Lyapunov exponents are continuous. Then we can say absolute continuity. Namely, the push-forward measure of this parameterized family of Gibbs measures will be absolutely continuous for Lebesgue almost every parameters. For those parameter values, this entropy over Lyapunov exponent ratio is strictly larger than 1. And basically, this proof here is not trivial, extremely technical adaptation of the result of Balazs and Schlag, which I already mentioned to you. So, since in previous examples, where I said that the natural projection, sorry, the parameter dependence of Gibbs measures on the symbolic space occur, where all of them Gibbs measures. So let me state then the Gibbs measure version of these theorems. So let's assume that we have a parameterized family of potentials where these parameters are exactly the same parameters as the parameters of the iterated function system. Let's assume that the potential is held uniformly with respect to the parameters, and the parameterization is also of the potential is also held uniformly, regardless of which infinite sequence you are checking it. So this basically means that all the previous continuity assumptions, what we were made here on the measure, this guy satisfies. The Gibbs measure, what you define. So if you are looking at this potential, it defines for you a unique ergodic shift invariant Gibbs measure. That Gibbs measure will have all the nice previous continuity properties, what I told you. So the push forward, the dimension of the push forward of mu lambda is the minimum of 1 and entropy over Lyapunov exponent for almost every parameters, and it will be absolutely continuous with respect to Lebesgue measure if the ratio of entropy over Lyapunov exponent is strictly larger than. Basically, in order to get this result, this absolute continuity result in the previous slide and here, this is where we really need that our parameterization is one-dimensional parameterization. This by we think, I think, but also we think that it's a kind of technical difficulty, but a very heavy technical difficulty. So absolutely not easy to adapt it for complete family of higher dimensional family of parameters. So we need this one dimension for this one, and also the larger smoothness properties of the iterated function system, like C1 does delta and so on, are essentially required here for the absolute continuity. So everything is, all the smoothness properties are to be able to adapt the result of Balazs and Schlag for that situation. All these smoothness properties are because of that fact. But let me state another result still in this world of parameterized family of Gibbs measures. Namely, if you choose your potential in this way, as we was discussing, this is the natural potential in the sense that this guy, the Gibbs measure with respect to this potential will give you the largest, the maximal entropy over Lyapunov exponent result, which will be S lambda, the conformality dimension. And in this case, if you're looking at those parameters where this S lambda is strictly larger than 1, then the push forward of this natural measure will not only be absolutely continuous with respect to the Lebesgue measure, but we will also know that it will be absolutely continuous with L2 density for almost every such parameters. So we can say something higher regularity not much really, but okay, we can say a little bit more than L2, just a little bit more, but it's not worth really to state. So, and for example, since the translation parameters are somewhat the most natural guys to occur, then here, who are the translation parameters who are natural, can occur and still one-dimensional? Well, it's the case when you have three functions. So by applying some rescaling and translation and some conjugacies, we can assume that your function system contains of three functions, where you just use your parameterization for the middle one, f2. And let's say you assume that all the functions are mapping the unit interval into itself, and the images of the unit interval by f1 and f3 are disjoint. If you assume that, furthermore, if you assume that the contracting ratios are at most 1/2, then this is a transversal family of iterated function system with one parameter. So whatever I told you works for this system. Okay, maybe it's maybe a good time to stop for a second and ask you that are there any questions or comments or something? Okay, if not, then let me continue with further examples, because we have a bunch of examples. One example is, which is in this incorrect paper appeared already, I showed you, is the place-dependent Bernoulli convolution. So what's that? This basically comes from the chaos game, but you can represent a chaos game with a nice dynamical system. Namely, let's take here well, this is not the unit square, but this is a kind of rectangle which goes from -1 to 1 here and from 0 to 1 in the y direction. Okay, so let's divide the square into two parts, a top part and the bottom part. Here the division is due to this straight line, okay? This rho x plus 1/2 function. But eventually this you could divide it into two parts by using any Hölder continuous functions. Okay, so and map the bottom part here in such a way that in the x coordinate you need to contract it by a factor lambda, and in the y coordinate you expand it in such a way then this roof goes to completely here up to y equals to 1, the line y equals to 1. So you expand on this part more to get the whole line here, to get this height, then here you expand here less. Okay, but you expand this weird shape here in such a way that you get this smaller rectangle. And you expand, you also map the top part in such a way that you contract and you factorize by lambda in the x direction, and you expand in the y direction completely for this light gray rectangle. So if you're looking at the dynamical system induced here, you can see the formula here. Then basically what you can see is that the SBR measure of this dynamical system is nothing else than the place-dependent probability measure. The place-dependent probability measure. So the stationary measure of my place-dependent chaos game. This is in the x direction. So in the x direction lives here the stationary measure, where these are the probability rho x plus 1/2, rho x minus 1/2 are the weights, my place-dependent weights. The Bernoulli convolutions are the functions of the Bernoulli convolution are my functions. This is in the x coordinate, and the y coordinate, you see the Lebesgue measure. This is basically true for general, not just for this example, this is true for general chaos game, place-dependent chaos game. So place-dependent chaos games can be represented by such kind of dynamical systems. However, the importance of this example is that, and this linearity of the probability weights are that in this case, we can estimate easily the entropy, which is required to be able to decide whether it's absolutely continuous or not. We know that the Bernoulli convolutions on this x-axis are transversal with respect to the contracting ratio parameter lambda between 0.5 and 0.66. Okay, and by estimating the entropy over Lyapunov exponent ratio, this light gray sector is where the SBR measure, and so in particular the stationary measure of this chaos game, is absolutely continuous with respect to the Lebesgue measure for almost every lambda values here. So imagine it in the following way: fix your favorite value of rho, draw a horizontal line, and on this horizontal line, Lebesgue almost every parameters for Lebesgue almost every lambda values will be absolute continuous. And this guy here is where the SBR measure will be singular, and that's strictly because the entropy over Lyapunov exponent ratio there is strictly smaller than 1. So this is how this absolute continuity and singularity map with respect to these slope and contracting ratio parameters look like. This is one example. Another example, which is also such kind of place-dependent probability measure, is the so-called Blackwell measure, which plays some important role in the theory of hidden Markov chains. So simplest example where we can see something is a simple Markov chain. So where the probability transition matrix is, so this Markov chain can have two values, 0 and 1. From the state, it remains the same 0 with probability p and goes to the other state with probability 1 minus p. This is your Markov system. And for a tiny epsilon probability or large epsilon probability, you add an IID noise. Namely, you see some noise with epsilon probability, or you don't see any noise with 1 minus epsilon probability. So if you join X and E together, of course, they will be still a Markov chain of 4 stages, depending on that which value X and E has. However, this is not what you observe. What you observe is the sum of the Markov chain and the noise. So this Zi, which is the sum, is what you see. You only see 0 and 1, so you have no clue whether this 0 is because of there was noise there, or this 0 is because there were no noise there. Okay, so this Z guy here is a hidden Markov chain, and Blackwell basically showed that the entropy of this hidden Markov chain, so this is a nasty formula. You don't really need to pay attention here for these nasty formulas, but what this means, is that Blackwell showed that the entropy of this hidden Markov chain can be expressed as a stationary measure with place-dependent of an iterated function system with place-dependent probabilities, where you can determine these probabilities by using these probabilities P and epsilons, and the maps here, and the maps here, S1 and S2 here, are rational maps. Nice rational maps. And that's the important, because since these were rationals, we could have some chance to show transversality. So basically, with Mark Polikon and Károly Simon, we determined this blue region in 2012 or even earlier, where basically it says that this entropy over Lyapunov exponent regime of this place-dependent probability measure, which is the place-dependent probability measure which can be used to calculate the entropy of this hidden Markov chain. So this entropy over Lyapunov exponent ratio is strictly smaller than 1. And with István Kolozsvári, we showed that in this red regime there, again, for every fixed value of, I think, P. Yes, I think so, because there are some kind of symmetry, but yes. For every fixed value of P, for almost every epsilon, we could show here the transversality in this red region. And of course, at that time, we thought that my result and place-dependent probabilities are correct. It wasn't, but anyhow, this system still satisfies the claims, the more smoother claims what we have now. Okay, and we have in this region, this red region, still absolute continuity for this place-dependent measure, which allows you to calculate the entropy of the hidden Markov chain. The white regions are the terra incognita. So here, the entropy over Lyapunov exponent region is ratio is strictly larger than 1. However, the transversality doesn't hold there, or we couldn't find any better parameterization to extend the transversality here. So we have no idea at the moment whether it's absolutely continuous here or not, but very highly it must be, almost surely at least, absolutely continuous. Okay. So these were the previous examples which occurred in our previous works. And now for the rest of the talk, let me give you some outline of the proofs. The easiest outline and the easiest to tell is basically the proof for the dimension result. Let me recall what were the conditions on the measure. The conditions on the measure was that it's continuous. So the measure of the cylinders is uniformly continuous in this sense of the parameters. Moreover, the entropy and the Lyapunov exponents are both continuous on the parameters. So this is such kind of parameterized family of measures. And then we can restrict, because we would like to see the entropy over Lyapunov exponent ratio at almost as a behavior of almost every point locally. So we restrict our parameterized measure to some Egorov set first. This means that you pick your favorite parameter value, lambda naught, and you take a teeny tiny neighborhood of it. And from now on, this teeny tiny neighborhood will be your parameter space. On this guy, we can define a set A lambda naught, capital N. Those infinite sequences of symbols where the lambda naught measure of the cylinder is close to epsilon, close to the lambda naught entropy, and the contracting ratio at lambda naught is epsilon close to the lambda naught contracting ratio, but for every n, we are greater than this capital N. Here comes the importance of the continuity of the entropy over Lyapunov exponents. Namely, if you chose this V here very carefully, this small neighborhood, depending on epsilon, then you would observe that that for every lambda from this tiny neighborhood, the union of these sets will be still 1. That's because the entropy at lambda will be epsilon close to the entropy at lambda naught. And that's why it also corresponds to these Egorov sets. So from now on, these mu lambdas are also restricted to this A lambda naught capital N. because after large n, it will eventually, for this lambda having positive measure. It's still an increasing sequence of sets on symbolics. Okay, but what's the important stuff? What we need to do here? Yes. Oh, something happened with my microphone. Oh God.
Something is wrong with voice.
Okay, just a second. Okay, just.
I don't have any problems. I don't know what is.
Yeah, but my microphone says that the correct one is chosen. So, Michał, do you hear me?
Yes,
I can hear you perfectly.
Oh, okay.
We hear you perfectly.
Excellent. So the error is most likely not on my side, maybe.
I hear everything you say without any change from the beginning of your talk.
So Felix, you cannot hear me now, I assume. Yes, I'm correct. He cannot.
You are muted, right? I'm muted. And are we muted in the main one?
You, I think, Balazs, you can continue because we hear you, but slightly weaker. So
Okay.
Yeah, but anyhow, we hear you.
Okay, good. So I'll then try to be a little bit louder, I don't know. So, because what's the usual strategy? So if you want to use the transversality method to show something, what's your usual strategy? Well, you say that if the Frostman energy of the measure is finite, then you know that the exponent here, this alpha exponent in the Frostman energy, will be a lower bound for the Hausdorff dimension. So if you know it for almost every lambda parameters, it will be finite. That if the integral of the Frostman energy will be finite, then you are still ready. And the usual tactic is here that if these mu measures, who are measures on the symbolic space, would not depend on the parameter lambda, then you just apply Fubini, exchange the integrals, put d lambda inside, and then you eventually see a formula where let me go there back. Károly uses two projectors, which is now would have been more convenient, but then you eventually end up in such kind of estimate, and then the transversality method works. But here, unfortunately, you cannot do that. So look at here. These mu measures depends on the integral, so you cannot apply Fubini theorem to exchange the integration by parameters with the integration on the symbolic space. So here you need some kind of approximation. So first, observe that by very simple change of the integrals, this basically can be written as an infinite sum, as an infinite series. It's a very, very standard way. But here you are integrating now the measure of those infinite symbols, omega and tau, who are 2 to the power minus n close to each other. And here comes the trick. Here comes the trick for that guy. Namely, use that this natural projection in the parameters is continuous. No, first not use that. First, restrict yourself in omega and tau to some first few finite words. Namely, since the contracting ratio, we assumed that our system is uniformly hyperbolic. We assume that the contracting ratio is independent of the parameter choice lambda. So that's why if I choose Q here sufficiently large, but independent of n, so this Q is not depending on n. This Q is just a horrendously large constant nothing to do with the n, in such a way that I restrict myself in omega and tau to the first qn symbols of omega and tau, and the remaining is just my favorite, let's say 1, 1, 1, 1, 1, 1, 1. Then this guy here, the natural projection of omega and natural projection restricted to omega up to the first qn symbols will be 2 to the power minus n close to each other. So altogether, these two guys, the distance of these two guys can be at most 2 to the power minus n plus 1. Right? Because this guy here, these two can have distance 2 to the power minus n, where this q just depends on the largest contracting ratio and nothing more. This guy is also 2 to the power minus n close to each other. These were originally closer than 2 to the power minus n. Okay, I miscalculated myself, since the distance here is 3 times 2 to the power minus n and not 2 times 2 to the power minus n. But anyhow, the importance is that this q is independent of n. And now, what did we do? We changed this set, which is a difficult set, to a simple set. This is just qn length cylinders, right? Nothing else. Decide whether the qn length cylinder is closer than 2 to the power minus n or not. And if it is, then we can change this lambda to lambda naught. And what's the price? The price is this e to the power epsilon times the length of the cylinder. The length of the cylinder was qn, right? And altogether, since we choose epsilon horrendously tiny and q is independent of everything, then this q epsilon will be still very, very tiny. It will be so tiny that this alpha plus q epsilon is still smaller than 1. This is why this epsilon prime is here, because we choose this epsilon prime accordingly to epsilon, with modifying it with some constant factors, in order to that this guy is still smaller than 1. And from now on, what do you see here? From now on, you see here this mu lambda naught. You see here this mu lambda naught measure. And this guy is not depending on my parameter lambda anymore. So here, what do I do is that now it's a standard transversality argument. I immediately apply here Fubini's theorem to see the Lebesgue measure of those lambda parameters where this is finite. Then the usual standard tricks for the transversality implies that this energy will be finite. And that's the trick for the dimension. So with this nice smoothness trick, you can, with this nice change of parameter value, you can get the result. However, and unfortunately, this is not the case at the absolute continuity. So how does the standard transversality proof of the absolute continuity goes? Well, you have this push forward measure, right? Let's say that now for some fixed lambda. Okay, because we want to bring it back to this lambda naught case, or parameter dependent case. Okay, so you are having here this lower density of the push forward measure with respect to the Lebesgue. Okay, then not Fubini. Which lemma? Oh God, I forgot which lemma is when the limit comes out from the integral.
Fatu.
Fatu, thank you. Yes, yes, Fatu lemma. Yes. So using Fatu's lemma, this limit comes out, and what we need to estimate is, thank you very much, Chris. So what we need to estimate is that this integral here in the middle is at most constant times r. Okay, and this is again just a usual Fubini putting the lambda, the parameter integral inside, and everything will be usual. But what's the problem in our case? if you are looking at this, that instead of lambda naught here, this lambda will depend on also the parameter. And you play the previous trick, what we played here. You look at here with this, oops, with this q epsilon extra error. What does this q epsilon extra error mean? That here, an extra r to the power minus epsilon is introduced. This is what it means. So instead of showing that this integral here is at most constant times r, we can proudly show that this is at most constant times r to the power 1 minus epsilon. But this is because of this limit factor. This is not good, because this side will blow up, go to infinity, and this is not good because we want to show that this is finite. So this is now to prove the absolute continuity, we need some more sophisticated tools, which are provided by Boris and Schlag. And basically, the essence of the tool was the Sobolev dimension. So what's the Sobolev energy? The Sobolev energy is something different, but in the sense of dimension, it's exactly the same. So let me define the Sobolev energy at alpha of a measure mu as follows. So you take the Fourier transform of the measure mu, take its square, and look at the 1 plus absolute value of psi to the power alpha minus 1. And the Sobolev dimension is the largest alpha value, just like in the case of force-bound energy and correlation dimension, that the largest alpha value for which this energy is finite. What we know is that if the Sobolev dimension is strictly larger than 1, then what happens is that this nu hat is, of course, the Fourier transform is in L2. Right? By definition, looking at here, this is Sobolev strictly larger than 1, then this Fourier transform is in L2. So, or measure nu must be also in L2 and absolute continuous. So our goal is to show that the Sobolev dimension is greater than 1. But in order to do and use this Sobolev dimension to prove absolute continuity, we need the Littlewood-Paley function, which is a function from R to R in the Schwartz class, which says that its Fourier transform is positive. Unfortunately, and very unfortunately, that what we require that its Fourier transform is positive with these desired properties. Okay, these desired properties says that just like previously in the Frostman energy case, we can approximate the Sobolev energy by this infinite sum. This is very similar as we did for the Frostman energy. But we need this Littlewood-Paley function to have these kind of properties. But this guy here, this phi here, is non-negative. So whatever tricks we were able to apply with the Frostman energy here, upper, lower bound, here we are not able to do. So we need extra efforts. And this extra effort is the following. So actually the strategy is that we are trying to show that the Sobolev energy, the integral of the Sobolev energy is finite. Using the previous change, what should have happened is that instead of here the lambda, we change it to a lambda naught. Exactly using the same tricks, namely that for a very, very tiny neighborhood, oh, sorry, this shouldn't be R, this should be this V, this tiny neighborhood of lambda naught, which is my fixed favorite parameter value. So instead of that mu lambda, I want to change to mu lambda naught in 2 steps. One step is that instead of general omega 1, omega 2, I restrict to it QN length words, so cylinders. On cylinders, by using the uniform Hölder continuity of mu lambda, I can switch to lambda naught and then switch back to omega 1, omega 2 by again using that this Qn, the Q there, is independent of n. But the problem is that unlike the previous case, it does not give us upper bound, because for some values this phi is positive, for some values this phi is negative. So we need to introduce an error term here. This error term depends on omega-1 and omega-2 and their first Q and finite many symbols. But then, I don't go into the details, but using this function, this phi and en together as a parameter of lambda, and lots of heavy technical bounds, which basically require the one parameter dependence, which require the extra smoothness of the functions. Along them, we can still prove that this energy here is finite. And basically, that's all what I wanted to tell you. Thank you for your attention.
Are there any questions? Maybe in the Zoom?
Let me
I
check.
see a question in the chat. Or maybe it's not.
It was earlier. It was earlier.
I'm checking the chat. I don't see anything on the chat.
Okay.
May I have a remark if there are no questions? Just
Absolutely, please.
So my name is Károly Simon, and I just like to mention that.
Kachi, just one thing. You are absolutely green, and I have no idea why.
I'm sorry. I'm sorry.
Yes.
Yeah. No, it's better. Thank you. So that there is one more application which I very briefly like to mention. That if we have application even for self-similar systems, there's a very simple self-similar system, namely which is contains of two mappings altogether. Mm-hmm. One of them is lambda1 times x. This is the function. You take x and you multiply it by a number, lambda1. And the other function is you multiply it by another number, lambda2, and you add 1. So the system is lambda1 times x, this is one function, and lambda2 times x plus 1, this is the other function. And this is, if you take this system as a two-parameter family, lambda1 and lambda2, then you ask about the absolute continuity of the natural measure. And this is very similar to the Bernoulli convolution situation, which was solved by Boris Solomyak. He had lambda times x and lambda times x plus 1. Here there is lambda 1x and lambda 2x plus 1. And our result gives the natural measure, the measure which is which belongs to this system. The natural measure is absolute continuous almost surely in these two parameters whenever it can be, namely when the entropy over Lyapunov exponent is bigger than 1. At least this lambda 1 and lambda 2 are not too big. They are within the so-called transversality bound. So this is an interesting application of our result, even in the self-similar situation, which is interesting because this is a two-parameter family, and Balazs spoke about one-parameter families, but nevertheless, this one-parameter family, the result implies something for the self-similar system of two parameters. Just as this comment.
Yes, thank you very much. I also need to mention that then here, not just absolute continuity, but L2. So you have L2 absolute continuity. And again, what you do is that in this regime, so this from 0.5 to 0.66 something in this cube, you fix one value, let's say lambda 1, and then you have transversality and lambda 2. This is, I think, what was shown by Neuhauser, maybe.
Almost. He considered this kind of families like lambda 1 and comma c times lambda 1. But
okay, yes.
Okay, it's doesn't matter. So it's similar.
Mm-hmm.
Okay. Go on. So this was my question. Who has a question? No more questions? Am I heard?
Seems so.
No more questions? Okay, let's thank Balazs again.
Thank you.